Okay, in this video, we are going to look at the reactions of nitrogen nucleophiles with ketones and aldehydes, and most specifically amines. Okay, so when we react a primary amine, like I've circled there, or ammonia, with a ketone or aldehyde in the presence of a very mild acid catalyst, okay, pH would be slightly below neutral, like 5 or 6 or something like that. What we'll make out of that is the imine, shown here, and a synonym for imine that biologists use, the Schiff base, but they really mean the same thing. And water is produced as a byproduct. Okay, before we go on here, let me just look at how we classify amines. Okay, so if there's one R group on nitrogen, it's primary. If there's two R groups, it's secondary. And if there's three R groups, it's tertiary. We'll discuss more about amines when we actually get to the chapter dealing with amines, okay? But we're going to specifically focus in this section on either primary or secondary amines reacting with carbonyl compounds. Okay, if the imine is treated with very strong acid or relatively strong base, that reaction will reverse itself and you'll go back to the starting compounds. Okay, so this is the equation. Note what happens here is that we replace the CO bond with a CN bond. Okay, and the R group that you have attached to nitrogen comes along for the ride. Okay, so that's the simple way to look at this equation. So let's look at these two examples here and try and predict what the product is going to be. Again, you should work it out yourself, pause the video, and then restart it so you can see the answers. I'm going to go right into the answers. All right, so when we take cyclopentanone and isopropylamine, we're going to get this imine here. Okay, again, all that's happened is replaced the carbon-oxygen double bond with a carbon-nitrogen double bond, and whatever was attached with nitrogen is now going to be attached, or the R group that was attached to nitrogen in the starting material is going to be attached to it in the product. Okay, in this bottom case, we still have a primary amine. Recognize that the alkyl group is cyclopentanone. It's not actually part of the ring system. The nitrogen isn't. So we're going to do this, and the imine that we would expect would be this. And in each case, we would need a slight additive here, a mild acid catalyst to enable this reaction to go. This is kind of a little bit of a controversy. I'll talk about it in the mechanism. There are many cases where you don't need an acid catalyst at all and the reaction works perfectly fine. Okay, these are some special imines. These are historically important. They arose back before advances in spectroscopy when it was kind of hard to characterize compounds, and ketones and aldehydes are very often liquids, but when you turn them into their imine derivatives, many of the imine derivatives that you form can actually be solid. So it was common practice 50 years ago to make a aldehyde or ketone, then make some sort of imine derivative and use that as a melting point characterization. Okay, so let's look at some special imines. All right, so this is an oxime, and this derives from a ketone or aldehyde reacting with hydroxylamine as the nucleophile. There is no R group on nitrogen. There's an OH group instead, but the same thing is basically happening. A hydrazone arises from a ketone or aldehyde reacting with hydrazine. Again, there's no R group at nitrogen, but there's another nitrogen here, and this comes along for the ride as well. The semicarbazide is very often a solid, and this comes from reacting, I guess, I don't know what to call this compound, Enamine or something like that. But anyway, if you take this starting material and the ketone or aldehyde, you'll get the semicarbazide. All right, let's look at the mechanism for imine formation. It starts out like many of the reactions in the ketone or aldehyde chapter. We have a nucleophile. This is the nitrogen lone pair. Okay, attacks the carbonyl group to generate this species here, which we'll call a zwitterion. It's neutral, but it has a positive and a negative formal charge within the molecule. Okay. This extra hydrogen here would be so much happier at oxygen that a self-neutralization takes place. Okay. You need the mild acid for this next step because we have to protonate the alcohol. Okay, I didn't have an arrow for that, but let me do that. Okay, and once this is protonated, it's a pretty decent leaving group. Actually, it's not decent. It's a really good leaving group. Sorry about that. The lone pair kicks this out. This generates a critical intermediate called an iminium salt. In many cases, these can be isolated, but with the extra amine present, it's just going to remove this extra hydrogen, and you're going to get the neutral compound. And this is a very favorable acid-base reaction. We won't talk about amine basicity until the amine chapter, but nitrogen at sp3 nitrogen is generally more basic than sp2 nitrogen. Okay, so this reaction should go to the right. Okay, a very common mistake, which I'm not sure is really a mistake, that a lot of people make when writing this mechanism, okay, is that let me just redraw this compound. I'm going to put the lone pair here. Okay, is that they'll go right to the iminium salt by just kicking out hydroxide ion. All right, in many cases of amine formation, this likely might very well be happening, okay, because there are a lot of cases, particularly hydrazone formation, where you don't even have to add the acid catalyst and it still works, okay. This is the officially sanctioned mechanism that's in all the textbooks, but I'm not sure that in many cases that this direct displacement of hydroxide group might be occurring in some of the imine formation reactions that are successful when you don't have an acid catalyst. Okay, if the amine is secondary, okay, we now involve the alpha position. And remember that when we draw these bond line diagrams, oftentimes we can forget the hydrogens are here, but this is the alpha position. We'll talk more about the alpha position when we look at base-induced reactions of aldehydes and ketones a little later. Okay. All right, so under the same conditions as imine formation, when you have a secondary amine, you make not the imine, but you make the enamine. Okay, so we now have a double bond. Okay, there's the alpha position. So we're taking, like before, carbon-oxygen double bond is going to become a carbon-nitrogen single bond. The groups that we carry at nitrogen are going to end up in our product, everything except the hydrogen there. And we're going to now make a double bond between the carbonyl group and the alpha position. We're going to make a double bond here. And we're going to end up with the product that you see here, where now the alpha position is part of a double bond. Okay, remember that. And if you don't have any alpha hydrogens, you can't make an enamine. It's essential that you remove one of those hydrogens so it can go from being sp3 to sp2. So right here, okay, I'm going to draw it as an asterisk. You go from sp3 carbon to an sp2 carbon. And of course, there has to be an atom removed when you do that. Okay, so let's look at some enamine forming reaction equations. Let's try and complete these two right here. Okay, so when we look at cyclopentanone reacting with this amine, this is a very common one used to make enamines. This is called morpholine. Okay, our product is going to be this enamine right here. Okay, recognize that there are a lot of alpha hydrogens in this molecule. If I removed one of these down here on the lower below the carbonyl group, I just draw the compound where the double bond was going down, but that's symmetry equivalent to what I actually have here. Okay, this compound reacting with diethylamine. Okay, recognize that we already have one alkene group in our starting material, so this means they're going to make a new alkene group. So we should have two alkene groups in our product, and that's the anticipated product of this reaction right here, the enamine that I drew last. Okay, all right, so let's look at the mechanism for enamine formation. What we're going to find out is that 75% or so of the imine and enamine formation mechanisms are identical. Okay? All right, so the nitrogen is going to serve as a nucleophile. Its lone pair is going to attack the carbonyl group to make this zwitterion shown here. We're going to undergo a self-neutralization to make this. Let's see, I forgot to tell you what we call this. This is called a hemiaminal. Okay, we're going to reversibly protonate the oxygen. Okay, and this is going to turn this into a leaving group. This is going to now make an iminium salt. This iminium salt is different from the iminium salt from imine formation because there's no hydrogen at nitrogen. Okay, look at this nitrogen right here. It has two R groups and a double bond. All right, so we can't remove a hydrogen from nitrogen. The only hydrogen available is at the alpha position. Okay, so we remove one of those hydrogens, and this produces our product. Okay, let me just say one thing I should have said in the previous slide. There's something that people might not like about this step here, and this is the fact that a nitrogen is a lot more basic. If you do a protonation, isn't that more likely? Well, it turns out that is happening to a large extent, but that reaction, all it does is just take you backwards. Okay, so 99% of the time probably, or more than 99% of the time, the H plus attacks nitrogen, but it cannot move forward if it does that. So every once in a while it'll attack oxygen, and that moves the reaction further to the right. Okay? All right, and we have in this last step, we're removing the hydrogen from the alpha position, okay, and this is a favorable process just from base strength, okay. We have the weaker acid-base pair in the final product, okay, so this will be the strong acid. This is strong base. Sorry, strong base. strong acid. Okay. And the reaction goes to the right. And again, you'll understand that concept a little bit better when we talk about amine basicity in the future. Okay. All right, so we're going to now look at a classic type of problem. For each imine and enamine depicted, determine the amine and the carbonyl compounds that are required to make it. All right, so and remember that your carbon-nitrogen bond it was a C double bond O in the starting material, so it's very easy to figure out the carbonyl group precursor to an amine. Just erase nitrogen and put oxygen there. Okay, and we're looking at the amine part. Recognize that when we made water, we've lost the carbonyl oxygen and we removed 2 hydrogens from the amine. So the amine part will have 2 more hydrogens at nitrogen. All right, so the amine and carbonyl are these two. Okay, the next one is an enamine. Recognize that at the alpha position that we had an extra hydrogen that was there that got removed in the very last step of the reaction. Okay, the nitrogen part, there would need to be. Okay, so what we would do is we would replace the nitrogen C sp2 bond okay, for the alkene. Would be a nitrogen-hydrogen bond in the starting material. Okay, so the compounds that we would need to make this particular enamine are, again, I've drawn here the iminium salt to sort of help you. Okay, the iminium salt was the second to last intermediate in the reaction. And here, if you look at this as being an amine, you can see that you would need this amine and this carbonyl group as a precursor. If you actually did this reaction, there are 2 possible enamines that you could get. So don't worry about the selectivity. We'll revisit the selectivity issue a little bit later in the class. But recognize that the unsymmetrical ketone that I have shown here gives you the possibility of making 2 different enamines. Okay, the forward reaction could have also made a different enamine as well. Okay, I'm trying to draw this. I hope I didn't overlap with where the next one is going to come down. Okay, not completely. All right, so this one is a amine formation reaction. There's some stereochemistry here. Recognize that the reaction occurs between nitrogen and carbon. This is the bond that we made right here. Nothing happens to the amine-bearing carbon. So we should not change the stereochemistry if we have an optically active or an antinumerically pure enamine form. Okay? All right, so the precursor amine is this one, and it should be the S isomer, just like it is in the starting material. Okay. And it reacts with the carbonyl group. Okay, we recognize that as being the same or the same task as in the very first one here. All right, this last one is an enamine, and remember that we have 2 hydrogens there. This is a bond line diagram, so our precursor compound needs to have 3 hydrogens there. Okay, So there's our iminium salt precursor, and we would eventually need the methyl ketone and this particular enamine right here. Okay? Sorry, that particular secondary amine. All right. So I think this is the last slide for imines. Let me just make sure. No, we have one more. Sorry. We're going to revisit an old reaction in the next slide. But the net gist here is that you make imines from primary amines and you make enamines from secondary amines reacting with carbonyl compounds. Okay? All right. Toward the end of the first half of the class, we looked at the Wolff-Kishner reduction, which back in those days, all you were using it for was to turn Friedel-Crafts acylation products into Friedel-Crafts alkylation products. Okay, one of the nice things about the Wolff-Kishner reduction relative to the other methods you may have seen, the Clemens reduction or the catalytic hydrogenation, is that all ketones and aldehydes will do the Wolff-Kishner reduction. It's not restricted to the phenylketones. Okay. All right, so what's the mechanism for this? Okay, let's balance the equation. All right, we add a little bit of nitrogen to the atmosphere when we do the Wolff-Kishner reduction, and we also make water. Okay, so there's the balanced reaction equation. All right, so recognize that these are not ideal conditions for imine formation, but it does occur reversibly under these conditions. So the first thing we do is we make the hydrazone. The hydrazone, in this case, has two hydrogens here. It's not all that acidic, but KOH and heat, these are very basic conditions, so we can reversibly pull off this proton, and this gives us this anion right here. All right, we can write a resonance structure for this anion, which is a carbanion. Okay, we're now going to protonate at carbon. This is going to produce this compound, which is known as an azo compound. These are stable if this hydrogen were replaced by an R group, this would be a stable compound, but with hydrogen here and with a strongly basic conditions, we can remove this proton again. Normally, this reaction is not favorable in an acid-base sense, but it's entropically favored. Okay, because it, obviously nitrogen, we turn one molecule into two, and the nitrogen-nitrogen bond is very strong. So this is driving this reaction. It's not good as far as acid-base considerations go, but as far as the overall thermodynamics, it's actually pretty good because it makes this very strong nitrogen-nitrogen double bond, and it's entropically very favored as well. All right, so this carbanion here is not going to have any kind of lifetime. It's going to be spontaneously protonated with the water that we have in the system, and it's eventually going to afford the product, okay? Here's our byproducts. We make water here, and we make nitrogen in this second to last step. Okay, so this is the end of this video. We're going to begin next time by looking at carbon nucleophiles, specifically the Wittig reaction.